up to this point, you've learned about cation exchange capacity and where it is derived from within soils, isomorphic substitution or pH-dependent charge. And we've talked about the units a little bit that are used for CEC, but let's talk about them specifically and where do they come from. So the units for cation exchange capacity that you most likely will see from soil testing labs is mill equivalents per 100 grams. This is the English units, and this is what oftentimes soil testing labs report CEC in. It's a strange unit. We're going to talk about why it's strange or why it's presented like this in this video. If you convert to the SI units, the units for the SI units is centimoles of charge per kilogram of soil. And if you want to convert between English and metric, it just so happens that they equal one another. 1 mill equivalent per 100 grams equals 1 centimole of charge per kilogram. They're equal to one another, which makes the conversion very, very simple. So what is mill equivalence? Or what is equivalence? Equivalence is the number of charges present on, say, a soil or organic matter surface or in the soil itself. It's essentially the number of either negative charges or actually the positive charges that a soil can hold. And the positive charges that a soil can hold really depend on the charge of the cation that we're talking about. So for example, hydrogen has a +1 charge, where calcium has a +2 charge. And so if a soil has a -2 charge, it's going to hold 1 calcium ion, or it can hold 2 hydrogen ions, right? And so when we express cation exchange capacity, we express it on a charge basis, not on an ion basis, because of the fact that all these negative charges in the soil can hold a plethora of positive charged ions. But we want to know overall how much positive charge a soil can hold. So we don't talk about atoms or elements specifically, we talk about charge. And that's the concept of mill equivalents or equivalent weights. And so in your notes, the definition of equivalent weight, and we're going to keep this simple for soil fertility because there's several definitions, but for soil fertility, the equivalent weight simply equals the atomic weight divided by the charge of that ion. Okay, this is what you need to keep in mind for the subsequent videos and calculations that we're going to go through. But the equivalent weight of any ion is simply equal to its atomic weight divided by the charge of that ion. Okay, here's some subsequent information if you're interested. So 1 equivalent equals 1 mole of charge. So an equivalent is based on the charge of the ion. And 1 mill equivalent simply equals 1 millimole of charge. Right? I know this is basically SI units, but that's the premise behind using equivalent weights or equivalents to determine cation exchange capacity. It's all based on a charge basis, or how many positive charges the soil can hold. So let's go back to this example that was shown in the previous video. You have this column here, exchangeable or estimated cation exchange capacity in mill equivalents per 100 grams. So how do we go from these values here, the concentrations of potassium, calcium, magnesium, and sodium in a soil, to mill equivalents per 100 grams? Well, we can do this, and it's not difficult. We know the weights of each one of these elements, and we know the charge of each one of these ions, right? So potassium has a +1 charge, calcium has a +2, magnesium is +2, sodium is +1. These concentrations from this report are in parts per million. That's the same unit as milligrams per kilogram. And all we need to do is convert from milligrams per kilogram, including the charge of the ion, and doing a little bit of math to get to the units of milliequivalents per 100 grams. So let me show you the precursor to doing this math. So how do we calculate equivalent weight of any ion? And in this case, we're talking about positive ions, right? Simply the molecular weight divided by the valence of that ion. And this is what we do. For univalent ions, ions of +1 charge, potassium, sodium, ammonium, etc., anything with a +1 charge, you determine the atomic weight by going to the periodic table. You don't determine it, you look it up. In this case, potassium is 39, sodium is 23. And then here is the shorthand version. I like the shorthand version. I used to teach the longhand version, and I present the longhand version for those students that are taking this class online that want to see how I came up with the value. But the shorthand version is really simple. Simply the atomic weight divided by the valence. For potassium, it's 39 divided by 1. And the units that you end up in or with are 39 grams per equivalent. And if you want to convert this, it's the same thing as 39 milligrams per milliequivalent. It's just a unit conversion, right? There's 1,000 grams per milligram, and there's 1,000 equivalents per milliequivalent. So the value stays the same. Here's the longhand version, if you want it. If you want to write this down, you can pause this slide at the right now, or you can pause it at the end. Here's sodium, the shorthand version. The atomic weight of sodium or molecular weight of sodium is 23. The valence is 1. So the equivalent weight is 23 grams per equivalent or 23 milligrams per milliequivalent. These are the units we need. There's the longhand version. You do the same exact thing for +2 or divalent cations and +3 or trivalent cations. And here it is listed here. Here are the divalent cations. Anything with a +2 charge. Let's pick on, in this case, calcium and magnesium. Calcium has an atomic weight of 40. Magnesium has an atomic weight of 24. So the shorthand version for converting from atomic weight to equivalent weight for calcium is simply taking the atomic weight divided by the valence or the charge, 40 divided by 2, which equals, and we'll jump to the final units, 20 milligrams per milliequivalent. You do the same exact thing for magnesium. 24 divided by 2 equals 12 milligrams per milliequivalent. For the trivalent cations, such as aluminum, maybe iron +3, you simply take, and I'm sorry, I apologize, I didn't put this in red, but the atomic weight, in this case, aluminum's 27, and it has a charge of 3, and the equivalent weight is 9 milligrams per milliequivalent. Okay, so I'm going to stop with this section here. You can hit pause and write all this out, and then we'll jump into a calculation with the next video.